That's it. Yeah. Okay. So, good morning. Yeah. Sorry for the delay. I just flew down to Chennai and then I entered the wrong classroom. So I apologize for that. Okay. So, how do we begin? So I presume this is lecture number what in this course? You had a week of so you guys did some entanglement and some basic introduction to quantum mechanics, right?
Online.
Yeah. So how do I address the online people?
I just want to make sure because we're on Zoom call.
People are online.
Yeah, that's fine. But how does that matter to us?
I think if you're unmuted, you can just ask them, they will respond. You can hear them.
Oh, okay.
Just ask them if they are online. You will hear them.
I see just my screen. So
you just ask them if they're online. You just ask
are you guys online?
Which means they're not able to take.
Yeah, we are online.
Good. Oh, okay. So we will start very slowly. Really, it shouldn't take us 2 lectures for it, but yeah, please feel free to ask questions. So, and yeah, first of all, we'll be looking at basics of parameter estimation. Now, you don't have to write anything, by the way, because I'll be anyway sharing things. So, I mean, the natural question arises that what should quantum mechanics have to do with precision measurement or parameter estimation? See, ultimately, very intuitively thinking, if you're going to measure something very precisely, eventually you will go down to the uncertainty principle that you cannot have the position as well as precisely the momentum up to some resolution, which is the Planck's constant. And suppose you want to measure something like a gravitational wave which occurred 2 billion years ago, and the ripple in the space-time is so tiny that actually it's getting to that limit of the Planck's constant. Then it's of fundamental importance to us how quantum mechanics limits any sort of a parameter estimation. Can we actually use quantum mechanics to make our measurements more precise? So it's about both quantum mechanics as something that puts us in a jail, and also quantum mechanics as a liberator. So that sort of is the idea. So of course, it's a whole field which started. The main motivation was gravitational wave detection, and people were trying to devise and also figure out how quantum mechanics is going to trouble parameter estimation. So it's a very well developed field. We'll just have a glimpse of it in these lectures. So how does one measure any parameter? So if you think about it, any measurement involves measuring a change. So, for example, if you measure a temperature, your thermometer would change from the initial reading to the final reading. Anything would involve measuring some sort of a change. So, for example, let's say I'm measuring a mass of a cricket ball. By the way, I hope my writing is okay. Okay, so one way to do it is that I have a spring, which is my probe. So that's just a spring. And what I'll do is that I'll just hang the ball from the spring, and then the extension of the spring from its initial position is going to give me the idea of the weight. Heavier the ball, the more my spring is going to elongate. So yeah, so this is a change. And then I have a measurement. So based upon these measurements, I do it many, many times. I get n length, which is going to be the elongation of the spring. And then I put it through some estimator function. This function basically takes these guys as inputs and pops up the value from which I'll estimate the mass of the cricket ball. There's a chat message I'm seeing. Should I be accessing it right now? Ma'am, there's a chat message somewhere. So should I just click it?
Yeah.
My fear is if I click it, then no, it's fine. But we'll lose this thing. Okay. Good morning, sir. Okay. Good morning. Okay. So how do we go to the next page now?
Scroll it up, I think just push it.
No.
Just push it up, I think move it to the scroll with your finger. You can.
Well, it's zooming basically. Wait. So.
Plus,
No. You can come. Sorry about that. So this plus. No. But how do we make the? Okay, that's fine. Now, where's the plus sign? Okay, this is the new page, is it? Okay. Okay, so basically, so this was a classical example of measuring something. Well, quantum mechanically, we'll pretty much do the same thing. So, I'll use quantum states as probes. So I'll have quantum states as my probes. So essentially what's happening is that I'll have an initial state and that is going to undergo a change, like our spring underwent a change. And as a result, the state is going to change itself. And so this was my initial state. This is my final state. And how much change the state has been caused due to the parameter. We are going to build up statistics, make measurements, M1, M2, Mn. And then you're going to estimate the parameter.
There are two different states, right? It may be eigenstate or some other state.
Good question. It matters. We'll come to that. If it's an eigenstate, there won't be any change.
Because it will be just scaling up.
Absolutely. Yeah. So that's a very good question. Thanks for asking that. Yeah, we'll come to that. It's important. So typically what we do, one way to sort of make this problem more concrete is that, let's say I want to measure a frequency omega. What I'll do is that I am going to embed that frequency in a Hamiltonian. So Hamiltonian is the operator that gives the time evolution of a quantum state, basically. And yeah, so typically I'm going to pick h bar 1, just a convention. So what do? Let's visualize it on the block sphere. I have, let's say, I start over here, or the spin up. And this is my step number 1. Now, as you said, this was the eigenstate. So that's not going to help me much. So what I do is that in the step one, I take my initial state and I rotate around the block sphere. So this was Y, this was X, this was Z. I rotate around the block sphere and get it to be aligned with the x-axis. So that's called as a pi/2 pulse about the Y. And I get, so I'll be using the top spin, up spin, or zero interchangeably. It just means the same symbol basically. So you can write it depending upon what your taste is. Both essentially represent the same state. I'm applying Hadamard or a rotation, essentially a rotation. So now I have the state which I'll call as 2. Now if I evolve the state through the Hamiltonian or the unitary operator, and mind you, H was given again by my half H bar omega tau over here. So now I evolve the state by U. What's going to happen? The state is going to, so my, there was one, I think, sigma Z also here. So this was sigma Z. Yeah. So what this Hamiltonian is doing, this Hamiltonian is a rotation about the Z axis. So this state is going to rotate about the Z axis somewhere over here. Okay. So that is my state 3. Somewhere over here I get, and this is just a unitary evolution over here. Essentially means a rotation in the Hilbert space. And what's going to happen is that my state is going to change to this thing. So this was my 3, step number 3 over here. So notice what has happened. I wanted to measure the parameter omega. The information of the omega is somehow mapped into the state, how much the state rotated by what angle. Now, if I make a measurement in the Z basis, I'm again going to get probability half and half. Now, the creativity or the trick is to again use this information which is hidden in this state and extract it out of some measurements. So the idea is to convert this phase. So what has happened is that these two has a relative phase between them. The idea is to rotate it again to map the phase information into amplitude information. And that is the hallmark of all quantum metrology. In fact, a lot of quantum information processing you're going to do. You're going to embed the thing in a phase, and then you're going to extract this phase information again back to the amplitude information. So what I do is that I again apply a rotation. You can even apply it minus pi/2, I think. So you can just check my calculations. I think I apply the minus pi/2 rotation, doesn't matter. I'm again flipping it up. And this state goes to somewhere over here. And if you calculate it, it comes out to be by this rotation. So this was my rotation. So that is my state number 4. Now you see if I measure the probability of being in the upspin or the probability of being in the downspin, they are different. And they're different depending upon what the value of omega is. So I've converted the parameter I had to measure omega first into a phase information, then into an amplitude information to measure what's going to happen. So okay, so now again, next page. Okay, So my state number 4 on the block sphere was this guy was if I measure the upspin, the probability of measuring it in the upspin is good. I just write it down as, doesn't matter how I write it. And the downspin is of course, quantum measurements are probabilistic, so I have to do this experiment many times to get an estimate of the probabilities from which I'm going to infer omega. That's the idea. Now the natural question is that how do we characterize or benchmark any metrology scheme? We are approaching fundamentally is any technique of quantum metrology superior to how I do metrology classically. So this will be clear what do we mean by this sort of a question, but that's the idea. Like, quantum mechanics has given us an advantage to cryptography, to computing, faster algorithms. Can it give us some sort of a more precise measurements? That's the idea over here. So to answer that question, essentially, first we'll have to delve. So this was the motivation, what we are doing, starting from a spring mass system, what do I mean by a parameter estimation, to how a quantum state itself is a probe to measure something. Now we'll have to build up a little bit of basic about parameter estimation and to make this question more concrete. So let's go to the statistics of parameter estimation. Yeah, so we are just building some basics for it. So the idea is that one has to make several measurements. And from these statistics, we get statistics. And we flip these statistics to infer the parameter. We already talked about it. The function that does it for us is called an estimator. So estimator is a function that is going to input all these values, x1, x2, x3. And eventually is going to give us, in our case, it was a mass. This was the extension of the springs, for example. Okay, so how well is our measurement protocol doing? How well are we doing in estimation process? One way to characterize this is to capture the variance of this quantity. So essentially what we are doing is that we have the estimated value minus the average over all these values, and we compute the variance. Now you might ask, why does the variance capture the estimation process? See, essentially what's really happening is that, let's say this was your unknown parameter, x0. And I make measurements, tick, 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 tick. I keep on making the measurements. I'll get some sort of a distribution. Let's say it's a Gaussian, doesn't matter, but this was the value of the true value, I can say, the value of the true value of the parameter. and I can plot histograms, make a probability function, and what's really happening is that how well I'm doing is characterized by this variance. So imagine you were doing the measurement so well that you instead had a delta function. That means, you have a brilliant measurement. You have so much information of the parameter from your measurement record that you are actually able to precisely locate the parameter over there. So that would give you an intuitive idea why variance is an important quantity over here. So yeah, this I can say this is experiment number 1. This is experiment number 2. So that was one essential part. There are 2 very minor issues with so far our scheme. One issue is that so the 2 issues, again, these are sort of technical points, 2 issues which we should clear right from the start, is that even if our estimator has a small variance, even if the estimator has a small variance, it can be systematically biased away from the parameter. Am I writing too fast? That's why it's sort of am I clicking it or something? Okay, so hold it back, is it?
No, when you write it, you can write it, but if you click, then that's an error.
I see. Okay, so even if the estimator has a small variance, it can be systematically biased away from the true parameter. So for example, you got a very narrow peak over here, but your calibration is an error. The true parameter was somewhere here. That can be, that happens all the time in military or something where, they want to hit a target, but it's a systematic bias over there. The second thing is that, as you would have already guessed, the estimator has different units from the actual parameter. So in our case, we were measuring the length of the spring, but eventually we wanted to measure the mass. So the units are different. So the estimator has different units from the actual parameter. Yeah, so then we still need to make sense of the variance in that sort of a thing. So both these things are, quite easily fixed. So I just give an example. That's for our example of the mass in the spring. We got the statistics about the lengths of the elongation of the spring, and ultimately we wanted to figure out the mass. So ultimately my estimation had the input of the lengths, and it had supposed to give me mass. So I just make some proportionality constant over here. This is one example. So how do I fix that? I just have the estimate of the mass divided by the estimate of the length. This factor is going to give me the value of lambda. And as someone said over here, it's just a scaling problem. So this will actually take care. This scaling factor is going to take care of the units of the lambda scaling factor. Of my estimation process. So my remedy for both these problems is that I define a new variable, which is my estimate divided by this derivative, which basically fixes the units. And this subtraction takes care of the calibration. Let's say this was some value of the parameter where I did the experiment, I tested, okay, this is my systematic bias. Then for all the experiments, I'll have the same systematic bias. So combine this new random variable takes care of both the things of my estimate. One, it fixes the units. Other, it takes care of the systematic bias over here. So now I'm going to be concerned about the variance of this guy. Yeah.
Like mass directly proportional to. Like, how do we know that it's directly?
So this was my assumption, but eventually this derivative is going to take care of that. That's the idea, actually. Even if there are different units, it's going to scale like that. So that's why we took the derivative. Mass spring is just a canonical example I'm running through one sort of an example to explain a lot of abstract mathematics or something like that. So, but the bottom line is that, so these were not very profound issues. They are just units issues, scaling issues. And ultimately, this is what we want to focus on, the quality of our metrology over here. Now, let's come to our example over here, which to remind you again, we did what we did. We prepared the state, we rotated it, we evolved the system through a Hamiltonian where my parameter was hidden. I got the information of the parameter in terms of relative phases, and I rotated again to get the phase information into the amplitude information. So the question is, okay, I need to, yeah. I'll just take the chat. Yeah, so Ritvik, the systematic bias, we are assuming it to be a constant because that's sort of, if you do an experiment or something, that's a calibration error. So we are right now treating the systematic bias as a constant to calibrate it. If the systematic bias itself is a random variable, then we need slightly more sophisticated things. It can be done, but then your parameter estimation has two random variables. One about the measurement itself and another random variable about the systematic bias. But my impression is that that's just going to be an extension of the parameter estimation. It would be a multiple parameter estimation problem, not very hard to solve. Over here, we are taking a very canonical example to see how quantum mechanics can improve our, let's say, parameter estimation in case, let's say, I have a systematic bias. So that was just sort of a technical point over here. But yeah, I mean, systematic bias can be all the time. It can, vary about. I mean, as a matter of fact, there's a project over here at IIT from DRDO that, in rain, wind, everything, the guns we have in the army, they lose their thing because the bias always changes. So they want to apply machine learning. Instead of sitting in earlier times, the army people used to sit with a big manual. If this is the temperature, this is the rainfall, this is the wind speed, that should be the calibration of the gun. Now they're sort of, trying to use artificial intelligence to sort of, systematically do these things. So, but yeah, I mean, we just take into account for all it means you can even take this systematic bias to be a function of time. I don't care, but that's the idea to fix the problem. Okay, so once again, I'll represent this quickly in terms of the language of a Ramsey interferometer. So Ramsey interferometer basically is essentially, so a Mach-Zehnder interferometer, basically you send light through the arms of the interferometer, you see the relative phase shift, and you measure some statistics. In a Ramsey interferometer, you actually send particles like atoms. But conceptually, mathematically, it's sort of the same thing. So we are going to just represent it. I have this ground state of the atom or something. I send it through the arms of the interferometer. Again, I have the pi pulse about the y-axis. Now, these are the two paths taken by the interferometer. Now, these are, in case of the Ramsey interferometer, they are not real paths. They are happening in the atom space. But it's easier to visualize it, what happens to these two superpositions which I'm creating over here. So I have this guy over here. Then I have the Hamiltonian. And then through this Hamiltonian, it's picking up these phases. It's a coherent superposition of the excited state and the ground state with relative phases. So this was my state number. I think it was, we called it 1. This was 2. This was 3. And then I make these guys rotate again through some pi/2 pulse. And I got this guy. So as I said, the probability of measuring the upspin was and the probability of measuring the downspin was I'm making a mistake somewhere. Okay, yeah. So what's the signal over here? The signal I'm getting when I'm doing a measurement over here is the expectation value of sigma z. That's my signal. In quantum mechanics, if you are familiar with the postulates, I make measurements, and the one thing I measure is the expectation value. The initial projective measurements are random, but I'm confident about what's the expectation value of sigma z. So this is the signal. And what's my noise? So noise is essentially the variance, shot by shot variance I'm seeing in that measurement. And that, if you look at it, is, so what's the expectation? So I have probability of spin being sine square omega t/2, probability of downspin being cos square omega t/2. If you calculate the expectation value of sigma z, it's going to turn out to be minus cos omega t. Yeah, it's just, basically, it's just quantum. I mean, it's just a, so this guy is somewhere on the Bloch sphere, this state. Finally, this was somewhere on the Bloch sphere. And I'm going to measure the expectation value of sigma z. This just turns out to be minus cos omega t. If omega was 0, this would have been 1 or minus 1, depending upon that sort of a thing. So depending upon the value of omega, that's what I'm getting. Yeah, so I hope this step is clear to everyone. What I'm doing is that probability of spin, value of upspin, plus probability of downspin, the value of downspin. And that turns out to be minus cos omega. That's what I'm doing. So the noise I'm getting, if you do the same thing and calculate the variance, the noise, what I'm getting is essentially, if you do the calculation, that turns out to be over here. That's a noise I have in the system. And as you can see, if omega is 0, there's no rotation, there's no variance, because we are measuring it in the eigenstate. Every time we get the same thing, that sort of thing. So essentially, if we apply our technology of the parameter estimation, which is essentially my variance of the estimate divided by the derivative of the signal times omega tau. And I do this experiment many, many times. I send one atom, I send second atom, I send third atom. So the whole thing is going to go as square root of n. That's just a classical standard limit, short noise limit, what people call as a short noise. This guy was, I believe, what we calculated to be cosine omega t. And this guy was also cosine omega t, because this was a derivative of sine. So one guy was cosine, the other guy was, the noise was sine, whose derivative was cosine again. So basically, essentially, my scaling goes as 1 over short noise. So this is the classical, even though I was using quantum mechanics, quantum probes, I couldn't do any better than a classical scaling. I was just getting a square root of n, 1 over square root of n short noise. But the question is that, can we do better?
is this because the measurement is a classical thing, not a
Measurement is quantum. Measurement is very much quantum. There's nothing special about measurement we are making. It's a random quantum measurement, and that's why we took this variance as well. Why this is happening, why we are only getting classical, is not an interesting question. The interesting question can be whether we can do better than classical. You can do something absolutely ridiculous and get no classical advantage. I mean, no classical advantage with the quantum system. Even in a quantum algorithm, if you keep measuring the quantum state, break all the superpositions and all the quantumness, or not able to harness the quantumness, you might end up with something very lousy. And that sort of is the idea. The question is that can we be more creative with the kind of resources we have quantum mechanically to do better than that?
I have one point. Already we have this in physics terms. We have the problem with the interpretation of measurements. There are different interpretations of measurements. Interpretation. Sometimes we have shut up and so we ourselves don't know how precisely to define a measurement. How can we use a measurement to in this estimated time?
Yeah, but see, all those measurements. See, there's a difference between having an opinion and measuring something in the lab. So physicists are mainly concerned about, physicists are concerned about philosophical questions also, but you can't argue with something which you can actually map it to a number line, right? That is no longer an opinion, that is something measurement. So whether you talk about any sort of an interpretation of quantum mechanics, it has to agree with the lab. And it has been more than 100 years, and there hasn't been any single violation of quantum mechanics. So, this works. Absolutely. So this is sort of a philosophical argument about, let's say, a Bayesian or a frequentist approach in probability. A coin toss, does a single coin have a probability? Or you have to toss it 1 billion times to infer any sort of interpretation of probability. But, that's a matter of interpretation. When we toss a coin before a cricket game, we assume it's a random process. You don't have to do 1 billion times and get the probability or something like that. So that sort of is the idea. By the way, I'm pointing over here because I even eat my food like there. So don't feel that I'm not paying attention over here. So I'll probably, yeah.
So what do you mean by quantum advantage?
We'll see that now. Okay, so
instead of dealing with one atom, we'll deal with n atoms together in a single cell.
Yeah, that's the idea. So in this protocol, what we did was that we had some cavities, we designed our experiment, we were firing one atom at a time. And our resource, let's say I had a limited supply of these atoms, I got square root of n, 1 over square root of n, things like that. So the idea is now, let's see if we can exploit any property of quantum mechanics or, some, these exotic properties of quantum mechanics. So we are going to use entangled atoms. So instead of sending one atom at a time, I'm going to use something called as a Schrodinger's cat state. So what's really happening is that I have got n atoms prepared. And I make them go through the beam splitter, or I apply the pi/2 pulse over here. So now what do I have in the arms of this interferometer? Which basically this is an interference or a superposition happening in the space of the Hilbert space of the atom. These are just our schematic to map the optical interferometer to this Ramsey interferometer. So I get a superposition of n upspins plus a superposition of n downspins. So this is this state is also called as a Schrodinger's cat state. If I manage to entangle the atoms, not entangle, create a coherent superposition of n atoms in upspin and n atoms in downspin, you can view this as the cat being alive and cat being dead. So that sort of it's a superposition, all up or all down. And now I have this Hamiltonian, the same Hamiltonian where now this Hamiltonian acts on each spin or each atom, it's acting on it. And so that's the idea. So now what I'm going to do is that, so this was my, again, 1, this was 2. And after the evolution, I'll have this state. Again, the value of the parameter is hidden in the relative phases. I have to again rotate it, flip it, and what do I get? I'll get again a term with sine and a term with cosine. But notice that now the term with sine and cosine has scaled by n. It is, in some sense, what's happening is a collection of n atoms in a coherent superposition is rotating n times faster. So if I was sending them separately, they were going at one frequency, and I was getting a classical lousy 1/√n limit. If I have a coherent superposition, each of these spins is picking up a phase. Those phases in the exponent are adding up, and the collective this thing is rotating n times faster. So this is the frequency is rotating n times faster. So what I'll get over here is, so I'll just write down this thing. I'm getting, so okay, I'll just, what the heck. I rotate it again, take it up the block sphere, complete it in the amplitude, and I get a factor of sine all up plus, yeah, got you, thank you. And now if I calculate my probability of all up, and all down, I'll get, that's my thing. So my signal in this case is the expectation value of the collective Z observable on all n spins. And that basically gives me cosine n omega tau. And the noise came out to be, yeah, this is just algebra. And what's happening to my measuring the parameter, I have the noise divided by the signal. I take the derivative. And notice what's happening to this derivative over here. My signal was n times. And the derivative I take, that's going to pick up a n times things over there. So this is going to scale as 1/n. So it's quite terrific. Sending individual atoms or entangling them or making a, I keep saying entanglement interchangeably, making a giant superposition of them as a Schrodinger cat state is improving my scalability square root of n. So I'm getting a benefit of, so remember this was the same benefit you guys did Grover search algorithm. So you got a quadratic speed up in Grover search algorithm. And in some sense, quadratic speedup is the most optimal. You can prove that you can't make a unstructured search faster than the quadratic search. Think about it, why you cannot. But it's an interesting, there are several ways to prove it. But the question is that over here also you got a square root of an improvement from a classical protocol. The question is that, is this the most optimal you can do? Now, we already showed a quantum enhancement to metrology. And actually it turns out, yes, I mean, there have been experiments where people have gone to N3/2 as well. So, and this is actually quite a tremendous improvement in some sense, so right now, probably from this year, the gravitational wave detection, which got a Nobel Prize probably 2 years ago, now they would be starting using these quantum enhanced technology for, measuring. Over there, they are not dealing with Ramsey interferometry. They're dealing with optical interferometry. They're sending in squeeze light. But the idea is to use some non-classical feature of light to get an enhanced precision metrology over there. So that's the idea. And it's actually very essential because laser power itself in a metrology scheme, that's a resource. You can't have, unlimited laser power. So if you are restricted by the laser power or the number of photons going inside the interferometer, you better use it cleverly, quantum mechanically, to make some sort of an enhancement over there. So that was the upshot of one scheme of quantum metrology. So what did we do? We did the basics of parameter estimation, how we contrast classical to quantum parameter estimation. We saw one way to measure the frequency using the Ramsey interferometer. By the way, I mean, Ramsey got a Nobel Prize for the Ramsey interferometer, so we shouldn't call it lousy. We are doing now years, decades after what Ramsey did. We know how to do things even more superior, in a more superior way to Ramsey. So yeah, so we use this second quantum revolution superpositions to, get a square root of an enhancement. So, ma'am, what's the time right now? No. I mean, like, I think I was done for the first lecture, first part of this thing. Yeah, I think it's 10:26. How much?
We have another half an hour.
Half an hour, yeah. So, yeah. No. So, yeah, I can take questions because we are not out of time, but I'm out of the material. So, huh? I can provide overview from the beginning. Okay, yeah. So this is recorded, by the way. So
this 1/n3/2. Something has to do with Bose-Einstein materials.
They have done experiments using Bose-Einstein condensates. The idea is that the goal of a physicist is to question our assumptions, what assumptions we make in when we were doing these things. So if you look at it, anything in quantum mechanics is the initial state, the dynamics, and the measurements. So this is the, in some sense, that's exactly what's happening. We made some assumptions about the Hamiltonian. The Hamiltonian we applied to get these frequencies was a very simple rotation Hamiltonian in some sense. And that's how the enhancement we got was square root of n. But let's say that Hamiltonian itself is a very special Hamiltonian. That Hamiltonian itself is so sensitive to the parameter that it's kind of giving a nonlinear effect inside the Hamiltonian over here. So that's the idea. You are using metrology with K-body interactions, what they call, where you have K particles interacting with each other in some way. So that way you can get actually higher than 1/n enhancement over there. So that sort of is the idea. That was the framework. Well, yeah, that's a good question. I mean, I think you should check out the papers by Morgan Mitchell. These guys probably did the first experiment of N3/2. Yeah, any other questions? Yeah.
Sir, whenever we measure, we do it by comparing with something that does not change, right?
Okay.
So I wanted to ask you, what do you think about time measurement in quantum mechanics, and how can is it possible to improve, get a quantum advantage in it?
Time measurement. Yeah.
Because like time is like not a operator.
It's not an operator. Yeah.
So like we use some reference for measuring time. So like how much can we improve?
Yeah, that's a good question, man. I mean, so are you talking about, so there was a talk in our institute only last week about these atomic clocks and how these clocks don't lose even a second in 15 billion years or something like that. So, and that has to do with very stable transitions happening between, excited state and ground state. But you're talking about measuring absolute time. What does it even mean to be measuring time precisely? I'll have to think about it. Yeah, I don't know. Yeah.
So in the measurements, this factor of t itself. So like for the best results, do we measure at some particular times or any time?
Yeah. No, we'll come to that in the next lecture. But that's the idea. See, what's happening is that you are getting these fringe patterns, right? And when the signal is going n times fast, then you're getting these fringe patterns. So at what value of this fringe you measure over here, that certainly does actually have a role to play in this. That's a good question. Yeah.
So if it's too tight, then we'll see our average kind of thing. We couldn't see the details. The fringes are too tight.
Yeah, but I mean, our idea is to make the fringes. See, in some sense, what is frequency? Frequency is in some sense, it's an energy, right? Yeah. So, the higher the frequency of light, the lesser is the wavelength. So intuitively, if you look at even in this sort of a scheme, what's happening over here is using quantum mechanics, you're able to, wherever it went, I don't know. It was very equivalent to making it rotate at a very high frequency. So it's just like, it's the same sort of an analogy that you increase the frequency, you can measure wavelength much more precisely. That's, you're making it very precise over there.
So the problem, the doubt I had is if you are making it too tight, we see a very average kind of a pattern. Like
that actually depends upon what you are. So for example, your the orange shirt you're wearing, the color fluctuates from pixel to pixel, but it's the resolution of my eyes. I'm seeing an average orange color. So that's sort of is a difference, but that's my problem. If I had a better resolution, then I could see the difference between the pixels. That sort of thing. There are approximations where we take the mean field approximation, we do those kind of things. But yeah, we are not worrying about those things over here. We are just worrying about how precisely I can measure pixel to pixel or the resolution over here. If my probe itself is coarse grained or smeared out, then of course I'm going to see an average thing or something. There's a question over there. Yeah, sure. Yeah, please turn on the microphone.
Yeah, hello, Professor.
Hi.
Yeah, I'm audible?
Yes.
Okay, yeah. So good morning first. Okay, so my question is like the schemes that you were discussing over here. So like these are very close to in experimental regime, like most of these can be tested over lab.
Yeah.
Is there any way that we can turn this, study this metrological thing through quantum circuit? Because how we do usually in digital quantum computers, basically write codes on IBM Q and basically then, but here in the case, whatever you discussed.
Yeah, your question was halfway, like.
Sorry?
Can you? No. So I didn't quite get your question. So you're saying is that you want to study this through quantum circuits?
Yeah, is it possible or just we need a lab always to just do these things?
Okay, that's your question.
Because in the most experiment, because
Yeah,
in
yeah, yeah.
industrial settings, like
Yeah.
all the industrial companies will not be having a quantum lab. Rather, they'll go for some quantum services company where some companies will be providing their quantum computers. Basically, how
Yeah. See, I mean, certainly, look, these are ultimately circuits. As someone pointed out, this is a Hadamard, right? You might have some unitary operator over here. In fact, you should look at the paper. Carlton Caves wrote a paper in which he did not use a single equation, only circuit diagrams to explain entire quantum metrology. It's a very interesting paper where the paper only has pictures. Just write the name Carlton Caves and Google quantum circuits, quantum metrology. You'll find the paper, basically. So the answer to your question is the entire what we have done can be translated into a language of a circuit. There's no problem. And what is a circuit? You have an initial state, you have rotations, and you're representing the operation of a wave function. But my concern is that that's going to be a simulation of metrology, not metrology. So that's like playing FIFA on your video game, not in the World Cup. So does that answer the question? I mean, you can certainly do some experiments, but you won't be measuring gravitational waves through an IBM simulation. Does that answer your question?
Yes, thank you.
Okay. But yeah, I mean, you can make a circuit and probably get a benchmark of how. So by the way, what circuits we did right now of Ramsey interferometry or Mach-Zehnder, or so we did it assuming that there is no noise. You can make an IBM simulation. You can put some noise model, how these protocols are going to be affected by noise. So certainly you can do all sorts of exploration on an IBM computer. But yeah, I mean, this is not a real measurement on a circuit. That's what my limited point was. Not to say it's not useful.
Looks like there's one more question.
Okay. Please provide the name of the scientist. Okay, so his name is, Carlton Caves. I mean, these guys wrote the seminal papers in 1981, where there was this huge debate about whether or not quantum mechanics can actually do anything to improve the gravitational wave detection, whether or not quantum mechanics is going to, first of all, we should worry about quantum mechanics in measuring gravitational wave detection. And then, of course, this was very recent, where just Google quantum circuits and quantum metrology, you'll find a paper. Also, the nonlinear metrology I was talking about also is the same group. Yeah. And of course, you'll have, but yeah, this will going to give you an idea. Any other questions? Did we go too fast? Is my question. Did anyone get, especially the students out here, you got something out of it? Otherwise, please feel free to ask questions.
So if you like, we can take a break now and come back at if you're.
Yeah, that's fine.
But lunch is at 1, so. Right?
That's fine. Yeah. I think we'll be done sooner only. So. Okay. So yeah. So this was setting up the scene with what quantum metrology is. Can we get improvement in quantum metrology? And one sort of an example. The next lecture is going to be a bit more math. In fact, it's going to be a math lecture only. But yeah, I mean, it's just a matter of taste. The first lecture, you can think about it as, it's nice to talk about gravitation wave detection, Ramsey interferometer, fringes, things like that. these are our stories in physics. The next lecture is to sort of convince you that these stories are actually true. So that sort of is the idea. So we'll just have a slightly more rigorous treatment of parameter estimation classically, as well as we'll see how far we can go quantum mechanically. So that's sort of is the idea. But just keep this sort of an example in mind as sort of a template example.
So when do we read this?
What's the time?
This 10:40 now. So
10:40.
Do it 11.
11:10 is fine, or 11 is fine. 11 is fine actually. 11 is fine, but it has to be synchronized, right? Like
I'll make it 11:10 because.
No, that's fine. That's fine. I mean, that's not a big deal.
11:10.
Yeah.
So we can have 11:10 or 12:15.
Sorry, I didn't understand.
I mean, so the next lecture we can have it.
11:10, is it? That's fine.
Okay, what's your preference?
No, it's fine. 11 or 11:10 doesn't matter. Yeah.
So then we can announce for the online people.
So we will meet at 11:10. It's okay?
Yeah, sure. Thank you.
Okay, thank you. So I should stop the
We can have
thing or something?
stay in the adjacent room as usual.
It's done. It's stopped, is it? Okay, okay.
You're taking very bad. You take it.
So we need to unmute something or something? Yeah.
For sending the same email.
Who? You? I see. Bowling with right and batting with left, is it? Huh? You play shuttle. No. I mean, a lot of good batsmen, like great batsmen, they are actually ambidextrous if you look at it. Like Brian Lara, he throws with the right, he bats with the left. Ganguly, the same thing. Inzamam. And Sachin is a left-hander.
But bowls in right.
Yeah, but he's a left-hander actually, and there's a deeper reason for it. The elegance and control that comes from your top hand while batting, and if that's your hand of strength, it's actually good, rather than the bottom hand going on. So a lot of these people. I mean, cricket is a game of top hand. If you look at the Test cricket, people just bat like this and that sort of thing. So if this is more powerful, then it's a good thing. So yeah, my extracurricular activity is physics. Cricket is my first passion. So yeah. So okay. Can you hear me, people online?
Yes, sir.
Okay. Okay. So, yeah. So, this lecture is going to be, yeah, we'll just, whatever we developed in the first lecture, the metrology scheme, we're just going to see it more mathematically. There's nothing more, there's nothing very special about it. Most of it is going to be algebra, but some good concepts in it. So the example is, so there are two ways of doing physics. One is a very operational way. Let's say you were in the 17th or the 18th century and someone came up with a steam engine. Now you know that it works. But a theoretical physicist would be interested why it works, or what's the mathematics behind it. So we already showed and demonstrated the quantum advantage. We mathematically showed it, the 1/n scaling. Now we are going to argue on some, put all that sort of a stuff on some mathematical rigorous footing. So, I mean, in physics, we make progress both ways. One is we go and try things, and then we figure out and understand why those things work. And that leads us to new directions. So, part 2. So what's really happening in the things we saw? We had the quantum state. The parameter was hidden somewhere. We evolved the quantum state. And in some sense, this was our probe. And we measured the change in the probe to get information about the parameter. So why is this very interesting? So have you guys done some previous lecture on distinguishability of quantum states? How many of you are familiar with? You can distinguish two orthogonal quantum states, but you cannot distinguish with unit fidelity non-orthogonal quantum states. So you sort of did it in one of the previous lectures.
Yeah, the idea,
Idea was given. Who was teaching that? Prabha told. Yeah. So essentially that's the idea. So fundamentally your change through your evolution if the parameter is very sensitive, you're not going to make the state orthogonal to itself. Hence, there was always going to be, you can treat them as two probability distributions, which are sort of overlapping with each other rather than two delta functions. So that sort of is the idea. So for example, let's say I give you an example of a problem of classical parameter estimation. So in this particular picture, quantum states are more like overlapping vectors. They are not orthogonal, or you can treat them as overlapping probability functions or wave functions, which are sort of overlapping. So for example, let's say I have a coin, which gives me the probability of heads as 0.55 and the probability of tails as 0.45. So this is my biased coin. And compare it to a fair coin, which is 0.5 and 0.5. Now let's say I make 100 coin tosses. How likely I am to mistake one coin for the other coin? Look, even for a fair coin, there is always a chance that I toss 100 times. 55 times heads can come and 45 times tails can come, right? So these are sort of overlapping probability distributions. Of course, I do this experiment many times, then it's going to reveal itself to me, what's really happening. You can't fool the bias so much. If I toss it 1 billion times, and then I get some sort of a probability of 0.55 and 0.45, then I say, hang on a minute, there's something wrong with the coin. Other than that, if I am limited by, I toss it 10 times. I mean, even in a fair coin, I can get 6 heads and 4 tails, right? So that sort of is the idea where we are going over here, is that to study, so metrology is about distinguishing quantum states which evolved through a parameter which was hidden. And this distinguishability ultimately is related to how close these vectors are to each other, or how overlapping these probability distributions are to. So this classical picture of distinguishing one probability distribution from another probability distribution is going to help us. That sort of is the idea. So yeah, so over here, the parameter could be determining the degree of this bias, for example. I toss 1 billion times, I get head 0.55 times. I sort of know what's the bias of the coin. That sort of is the idea. So yeah, essentially it boils down to distinguishing these two distributions.
In that sense, can we say it's related to more of the state's fidelity?
Yeah, quantum states fidelity, very true. But let's first define classically what's happening. Two distributions.
It's off topic question. It's just that
Yeah.
as we're predicting this, that is why it's called meteorology. Yes, whether Federer predicts it.
Yeah. No, it's not meteorology, it's metrology. Yeah. So yeah. I mean, the way we predict weather, it would be disaster. We are not at all precise. So, you know, I'm glad it's not called meteorology. So, yeah. So roughly, you know, that's what's happening. As I change the parameter, this probability distribution is changing a bit. Now, the idea is this information of the parameter was embedded inside this probability distribution. How precisely I can measure this parameter is how precisely I can distinguish these two probability distributions. And there is a very standard way of defining a distance between two probability distributions. How many of you guys know about this, the relative entropy or the Kullback-Leibler distance? So basically, it's just the distance between two probability distributions is, let's say, in first case, we have discrete probability distributions. It's just that's the distance. You can see this is also called as the quantum relative entropy. If they are exactly equal, then this guy becomes 0. So, you know, it's an identical distribution. Now, essentially, okay, so plus. No, the thing is that I'm only using half the page.
You can scroll down the side. Yeah.
Okay, that's better. Yeah. So over here, the problem was I had a theta, I had a probability distribution. I moved theta very tinily. So I am very interested in the distance of a probability distribution to a nearby distribution. In other words, is it the same page? Okay. Yeah. I'm interested in a probability distribution which is very tinily displaced from so Q is nearby to the distribution P. So we'll see the motivation of it soon, but the idea is that what is the distance of P to a nearby distribution? That I'm just going to expand my formula. I'm going to plug in the value of Q now. When I calculate so after that, this is just algebra. What I'm going to do is that I'm going to calculate the first non-vanishing term of it. And we'll see the motivation why we are doing this. So this basically becomes and I'm going to just use the log expansion of, let's say, log 1 over x was, yeah, use some series expansion. So when the smoke clears, what I get is I just expand this guy out, I get I don't bother about many higher terms because I'm assuming this delta Pj is so small, it's just a nearby distribution. So I'm going to just neglect the other terms over here. And that gives me what? That basically gives me a bunch of factors. That gives me a term delta Pj, plus that gives me, so this is just algebra. If you guys like me can't calculate that fast in your head, don't worry about it. Just, put it in Mathematica or something. So on and so forth. So what is going to be this term? Remember, I had Qi or Qj, whatever. Qj was Pj plus delta Pj. And I know Qj is delta Pj. Sum of, because these are probabilities, they have to normalize to 1. So the change is going to be 0. Sometimes going to be slightly more, sometimes going to be less. So this guy cancels out. I'm just left with the second order term. And I'll just going to solve it, and I'll just write down the answer. And the answer, basically, the idea is that Q was a nearby distribution to P. To the first non-vanishing term, this guy boils down to something like that. Of course, there are going to be some corrections. I am going to not bother about it, 2 over log 2, because remember, the way I defined the relative entropy was a logarithm, and my series expansion was a natural log. So there will be a correction of log 2 or things like that. Let's not worry about those things. Where did my, yeah. So yeah, over here I had a log. The series I was using of the natural log. So basically the idea is just focus on this particular expression. That's going to be, so what is this capturing? This is capturing the distance between a probability distribution Pj and a nearby distribution. Well, 4 over 2, so I can cancel. So this was 1 over 2 over here. And log 2 came from the correction of that sort of a thing. So don't worry about it. The idea is this particular quantity over here. Okay, so why is this quantity useful for us? So this is, by the way, this quantity is also called as a Bhattacharya distance. Or it's also called as the Fisher information. Eventually, our motivation is to connect the distinguishability of 2 probability distributions to parameter estimation. How close to the distributions are, or let's say I change the parameter by a very small amount, infinitesimally I change the parameter. how well I can distinguish these two distributions actually tells me how sensitive that probability distribution is to my parameter. For example, I had a delta function. I move this delta function, I can actually distinguish these two. They are in some sense orthogonal to each other. Whereas I had a very big overlap and I just tinily shift this function, I will mistake one for the other actually. So my entire information, how well I can measure a parameter, is embedded in these probability distributions. How well I can distinguish these probability distributions. So, well, we can translate this into the language of continuous variables also. There's nothing special about, yeah, we'll just take an integral. Over here. So again, what we just said in English, let's say my px was some probability function depending upon some parameter theta. So by that I mean is that I have a family of probability distributions depending or indexed by a parameter theta, and let's say I have a distribution qx, which is a nearby distribution. That's essentially going to be some derivative delta theta. The parameter is the same. So what is happening is that I'm trying to capture the notion how sensitive this probability distribution is to the parameter I have. So for example, in the case of a delta function, let's say my parameter was the mean. I change the mean tinily, the probability distribution becomes separate. And that's actually what's happened classically. Classically, everything is distinguishable. We don't have overlapping classical states. Classically, I can measure things fundamentally. In principle, I can measure things very precisely. A motion, there's no uncertainty principle. I can measure a pixel from the next pixel. There's no blur of information. What happens in probabilities or in quantum mechanics, actually. Quantum mechanics, I can have only orthogonal states. I distinguish them with unit fidelity. Otherwise, things are overlapping. So that's the notion we are trying to capture. So this was my neighboring distribution, nearby distribution. And now my relative entropy, when I calculate this sort of an integral, well, it's the same thing. I just expand this guy. I put in the log, and then I have got something inside the logarithm. Can I write q instead of f? Why? Yeah, so q, sorry, so you mean to say this thing, is it? Yeah, so that's fine, right? So it's clear, right? So q is basically, so my px theta was this guy. Q is another probability distribution, which is basically a nearby probability distribution. And I'm taking the relative entropy, which actually captures how sensitive is my probability distribution to the parameter. So yes, in fact, if you can look very closely, I'm actually studying the property of one probability distribution, how sensitive that probability distribution is to a change in the parameter. That's why I'm comparing it to a nearby distribution by shifting the parameter. That's sort of is the idea over here. So again, when the smoke clears, over here I had, I had this guy, some scaling factors, the correction term over the probability distribution. In the continuum limit, I'll get the same thing. What happens is that, well, let's just, if I can scroll down. Yeah, just do it again. Yeah, so just imagine we've given this problem to the math department, and I'm again just going to expand this logarithm as a power series. We probably might not even need that. We'll be happy with far less than that. This is just a simple generalization of what we've already been doing. So over here. So the first non-vanishing term over here would be, say, this delta theta. This is integral with dx. Delta theta just comes out, and I have got an integral squared divided by this guy, which was my Bhattacharya distance or the Fisher information. So this is the hole in the integral sign. So this is the expression of my Fisher information, which mathematically captures the following thing. If I have a random variable x and which has the hidden knowledge of a parameter, so I'm sampling this random variable through this probability distribution. I'm getting these outcomes x1, x2, xn. How much information about theta is hidden inside this random variable is captured by the Fisher information. And intuitively, what's happening? It's basically how sensitive my probability distribution or the distance between the nearby distribution is to the change in theta. The more sensitive it is, the better I can distinguish these two guys. So that sort of is the idea. So why is this quantity interesting to us? So, yeah.
The P and Q distributions, are we measuring the same quantity or are they different ones?
P and Q distributions are the, so our parameter is theta. So P distribution is the following. Okay. Our parameter is theta. So for example, I'll give you an example. Let's say I had a Gaussian distribution. Okay. Some Gaussian, you can sort of normalize it whatever way you want to. So that's my distribution. Let's say this was my, okay. My parameter is theta. So this is a distribution somewhere theta, right? Now, what is the distance between this distribution and a nearby distribution? I changed theta very slightly. What's the distance? So it might sort of go over here. Now you can imagine the lesser the variance, the better I can distinguish these two distributions. It's like, you know, when you image something without your glasses, both things become blurred. My glasses are sharp. Now I can see you as, you know, the features of your face as delta functions in my eye. And that essentially is the problem with my glasses or my lack of glasses or my metrology, seeing your face. If things are hazy, overlapping, the distance is less. I have less Fisher information. If I can distinguish things sharply, resolutions, my metrology is better. I can see you better. So we are capturing this blurriness, which we see in the language of mathematics, basically, as a distance between two probability distributions. And a more convenient quantity and a more physical quantity is to see the first order non-vanishing term, which is the Fisher information. That's sort of is the idea over here. So this is the basics of parameter estimation. In quantum mechanics, we just generalize these things. Instead of probability distributions, we have quantum states. That sort of is the idea. So that's the fundamental problem. We quantified these things, how well we are measuring things. Why does the Gaussian with a wider variance have lesser information than a narrowly peaked delta function? This is a way to quantify these things through these expressions, actually.
We are finding distance like or similarities or differences between two probabilities rather than applying something like KL divergence. Can't we like apply some sort of transformation to this?
Like what?
Anything like a power transformation or log transformation, which will like bring out the delta theta more efficiently.
That's interesting. I'll have to think about it.
So can you please, elaborate the question?
No, so he's saying that if you do some sort of a transformation on the probability distribution to see the sensitivity in a better way. I think probably that's your question, paraphrasing. Yeah. So that can be possible. Right now, my idea is to, see, there can be many ways of bringing out things together. But for our purpose, so here's our plan. We have one way to quantify how much information is there in a measurement record. So essentially what's happening is that I make a bunch of measurements. These measurements are coming from a random variable X, which depends upon a probability distribution. I am quantifying how much information is there in my measurement about the parameter. That's my goal, actually. And what measurement schemes are yielding me higher Fisher information? That sort of is the idea, what we are getting at, actually. So we can just summarize it that, greater my Fisher information, greater is the distance between two nearby probability distributions, which helps me distinguish them. Probability distribution functions. And intuitively, that means that it's more sensitive to the parameter being measured. Okay, so another way of writing the Fisher information expression, if you look at it, is the same thing. Is essentially it's just writing the same thing over again. Yeah, so this is exactly similar to our previous expression. You differentiate the log, you get a 1 over fx in the denominator, and then it would be a derivative of this function. One of them is going to cancel. So yeah, so this form is exactly equal to what we wrote earlier, which was the previous term. I think we wrote this thing. Yeah, usually this is the way people define, but this is exactly identical to this thing. Yeah. Okay, so another way of writing this thing, which is going to be slightly more intuitive to you guys, would be, again, you might do it as you can write also this in terms of the second derivative. Now, what does the second derivative do to a function? See, the first derivative measures the slope. The second derivative measures the curvature of the function. That's essentially what's happening. Fisher information is calculating the average curvature of the function, averaged over the probability distribution function. So the more the curvature, the lesser the, I don't know how to say more or less, the sharper the curvature, the more the Fisher information. That sort of is the idea. And that also shows you how sensitive the thing is to, how sensitive the probability distribution is to the parameter. So that's what is happening geometrically. This, these are equivalent, mathematically equivalent. Second derivative just gives you an intuitive way to see the curvature effect in some sense. So for example, we already discussed this example. I have this Gaussian probability distribution. Am I on the same page? Okay, yeah. So I am on the, so I had this guy, the Gaussian probability distribution. And if I calculate the Fisher information from either of these, any of these wonderful formulas, what I'll get is the Fisher information comes out to be 1 over the variance. which means the lesser the variance, the more the Fisher information. The sharper the function, the more the Fisher information. In fact, if it's a delta function, then the Fisher information is infinity. Well, I mean, I have precisely the information about the parameter I was supposed to measure. So what have we done? We have abstracted this notion of metrology or parameter estimation in the language of probability distributions. And from those probability distributions, how close that probability distribution is to a nearby distribution, depending upon the parameter, we've extracted out a mathematical quantity to capture how well we are doing. So you can roughly say probability distribution is my eyes like this, you know, it's a very, curvature is very, you know, broad. Now it becomes hopefully 6 by 6 a delta function or something. So that sort of is the idea. I'm having more Fisher. This is a better metrology scheme than without glasses. That sort of is what's happening. Okay, so yeah, so this was, you know, so if you have a series of curves, of course, this one has the most Fisher information. Okay, so there are some very interesting and very useful properties of Fisher information. So we already defined an estimator. You know, we were dealing with y-est, x1, x2 in our spring mass problem, which popped out a number mass over here. In general, in the jargon or in the parlance, I call it T is called as the estimator. So the estimator takes inputs of values, these x1, x2, x3, and it pops out basically the parameter theta. Estimator is a function which will take in the measurement record and give me the value of the parameter. What would be a useful quantity for an estimate? It's going to be the variance of the estimator. How well we are doing would be determined by the variance of my estimator, actually. And we won't prove this, but essentially the idea is that the variance of any estimator is limited or bounded by 1 over the Fisher information. This is called as a Kramer-Rao bound. Kramer-Rao bound. So I think this Rao is the famous Rao of, you know, the great Rao of Indian statistics. He's still alive. He's 102 years old. So I think statisticians live longer. So, and statistical physicists commit suicide. So it's a, yeah. So yeah, so this is the Kramer-Rao inequality that fundamentally I can have any function here. My function could be just measuring the first value. My function can be measuring the mean of all the values I get, just average out all my measurements. But fundamentally, my estimation process is bounded by the fundamental nature of the probability distribution I'm sampling from. What aspect of that probability distribution? The Fisher information. The more the Fisher information, the less is going to be my variance, the more precise is going to be my measurement over here. So that sort of is the idea. And, you know, Fisher information has some very nice, you know, that was one of the motivations of defining only the first non-vanishing term of the relative entropy as Fisher information. So another useful property is that if we have, I'll just take a question. Can Fisher information be used to put a bound on the number of weak measurements required to reconstruct a state? If there are any sources for this, could you point to? I see. Yes. Let's see. We should discuss this right after the lecture, because one good source is my own paper. So you can, I'll be delighted to talk about it. So yeah, we will definitely talk about it. Okay. Yeah, so if we have a sample of n random variables. So, you know, we had only one random variable in the first case. Now I have got capital X represents the random variable, n random variables drawn from an, you know, the same probability distribution in an IID, identical independently distributed. This guy, Fisher information is just additive. So Fisher information just comes out to be n times the Fisher information of one of these guys. So it's a nice property to have for an information metric that is additive. I do more things more times, it's just an additive thing. Okay, so this was all about distinguishing two classical probability distributions. These things can be very elegantly generalized to quantum case, where I have got quantum states, quantum wave functions, you can say, or and the problem boils down to distinguishing. Instead of distinguishing two probability distributions, I am distinguishing the quantum states.
More sense I can see that distributions differences in the amplitude.
No, but amplitude is just one of the things, in the sense that if you express the quantum state, let's say in the eigenstates of a Hermitian operator, each of the things will have an amplitude. Each of the basis vectors will have an amplitude. So yeah, in that sense, you can say that you are tweaking these amplitudes somewhere, all of them in some sense. Yeah. So that sort of is the idea. But essentially, what's really happening? So okay, next page probably. Yeah. So I have the initial state, which, remember in our probe, I had the initial state, which was probably, I had one state before this. And then I evolved it. And I got something over here. So this was my 1. This was my 2 on the block sphere. This was my 3 on the block sphere. And I got over here. So again, we have to capture the distance between this guy and this guy. Had I applied the Hamiltonian over here to the eigenstate, nothing would have changed. No distinguishability, no measurement, no sensitivity to a parameter. So eigenstates don't help us much. That's why we took the block sphere, we rotated it, and now through my evolution, I'm increasing the distance between these two states. And this distance, again, I capture it again going back over the block sphere. But essentially, even if you forget the measurement phase, the idea, the crux of the matter was to increase the distance between the probe from its initial position, rotate it, so that that distance I capture it again and measure the parameter. That sort of is the idea over here. So now, what's really going on? So how do we capture? So there are several ways of quantizing or making our Fisher information a quantum way. So in my interferometric setup, basically what was happening was I had this initial state and it went through. Then I had the Hamiltonian evolution. Then I again combined it. So, I had psi 0, psi 1, psi 2, psi 3. This was the measurement part. This was the measurement part. This was my, of course, the initial state. And I was able to create a superposition. And this was my state preparation part. And this was my dynamics. Now, one way of characterizing the distance between these two states is the following. So, for example, convince yourself that nothing happens to the eigenstate. So the distance between the eigenstate and the evolved eigenstate is 0. What is another way of capturing what I just said? I hit the state with an operator. It's an eigenstate that it doesn't evolve. What would be a good measure or a qualitatively good measure of the distance the variance, right? So if I calculate the variance, remember H was my Hamiltonian over here. If I calculate the variance of this operator, which is this variance captures the notion of the distance between. Nothing is happening in the eigenstate, and I am interested the set of states which gives the maximal variance. And essentially the quantum Kramer-Rao bound is we missed this part. Okay. So essentially the quantum Kramer-Rao bound is the following. The variance of any quantum estimator is bounded by, there's a factor of 2. Don't worry about that for now. This is my quantum Kramer-Rao bound. And this is one way to define my quantum Fisher information. Classically, the variance of the estimator was bounded by the Fisher information. Quantum mechanically also, the variance of the estimator is bounded by the quantum Fisher information, or how much variance the dynamics is generating, which actually is related to how further from the eigenstate I'm going actually. So that sort of is the idea about, and as you said, there are other ways of defining Fisher information, and a lot of them are very equivalent. So for example, one of the ways of defining Fisher information is, I think it was, so the 1 minus the overlap or the fidelity between the vector and a slightly displaced vector, and taking the limit like that. So if epsilon is 0, this gives me the distance would be 0. So how sensitive my state is to the parameter over here, that's going to distinguish these two quantum probability distributions. And essentially, if you look at in our entire metrology scheme, that's actually what's happening. So the quantum Kramer-Rao bound has 2 parts to it. So I have this variance of T. I'll just put the quantum Fisher information again, the factor of 2. One is the dynamics. So what can influence this variance? It can be the dynamics, some properties of the Hamiltonian, where we got this 1 over n 3/2 scaling. Remember, we talked about Bose-Einstein condensed states and things like that. If we design a Hamiltonian in a very funky way, usually we are dealing with independent Hamiltonians, H1, H2, where they're acting independently on each spins. We can sort of have a coupling of the Hamiltonian, something like to the power of k. So there would be some sort of an interaction, and this is going to lead to a higher variance. Or we can get an enhancement of metrology through quantum states, the state preparation. We saw the example of a cat state. We prepared the system in a quantum cat state, and we got 1 over n scaling. In a optical interferometer, so we gave an example of a Mach-Zehnder interferometer. In an optical interferometer, I have a beam splitter. This guy goes, I throw light from these ports, and I create an entangled state, something called as a noon state. Basically, that means is that either this state is a coherent superposition of n photons in the upper arm, 0 photons here, in a superposition with 0 photons in upper arm and n photons over here. And then I apply the Hamiltonian, it picks up the phase, and you can show, I think it would be useful for you guys to do this calculation. You can show that this also gives you 1 over n scale. It's exactly identical to the cat state or the Ramsey interferometry we did. This is just a Mach-Zehnder version of it.
These are different representations.
Yeah, and experimentally a lot different things. See, in the Ramsey interferometer, we represented things by interferometer arms, but that was our schematic. Everything is happening in the Hilbert space of the atom. Here, they are actual interferometer arms. This is like a gravitational wave detection, 4 kilometer arms. But yeah, I agree with you. The math is similar. So that sort of is happening over here. So either way, fundamentally, we need to create a difference between two probability distributions or probability states. Either we use initial state preparation, we use entanglement, we use superpositions, or we use some funky dynamics. The bedrock is distinguishability of quantum states and how sensitive we can make our probe to what we are measuring. And people are exploring things like trying to estimate parameters in the vicinity of a phase transition, for example. A wave function is very sensitive to the point of a phase transition or a critical point.
So because of
High correlations and things like that. So imagine if you are at the phase transition and just a tiny amount away from the phase transition, that would be a huge difference in wave functions actually. So people are exploring metrology scheme, but the bedrock of metrology is basically this, the mathematics we have described over here. So, people are using phase transitions, optical interferometry, atomic interferometry, so on and so forth. But that sort of is the idea of, the whole metrology over here. So I think we are sort of done here. I mean, I'm done. So yeah, I mean, I don't have anything more. Yeah. What's the time right now, Madhu?
12.
Okay, yeah.
We have got at least 45 minutes.
45 minutes, yeah, okay.
So basically, we can design. You told the reason you have to play with the Hamiltonian. Or
Yeah. Yeah. By the way, we didn't discuss the measurements out here. In the sense that, so we talked about the state creation, we talked about the dynamics. In general, there is a, I don't know whether it's a theorem or something, but one last thing before I would say I'm done is that, we talked about this Kramer-Rao bound. Yeah, which was variance is bounded by the Fisher information. Now, so far we were just dealing with the initial state and the dynamics and trying to see what's the distance between two vectors. Now, it can be shown actually that there always exists some measurement. There always exists a measurement that's going to saturate this bound. I don't know how to prove it, but I think you can prove it. Saturate this bound. Which mathematically means that, see, in our CAT state or the Ramsey interferometry, we measured sigma z. We inverted the population again, took it to a Bloch sphere, and we measured the population of top spin, the fraction of top spin, and the down spin. So that was, we were measuring sigma z operator for the Ramsey thing. What this thing says is that there exists a Hermitian operator, which is going to saturate this bound. Now, whether or not that Hermitian operator can be realized in a lab, that's another question. And that's also somewhere the creativity in metrology lies. Not every mathematical matrix, you can realize it in a lab. If you have photons coming through two arms of the interferometer, either you can do a detection of photons. What is the population in this arm versus this arm? Or you can measure some polarization. It doesn't mean that you can measure every measurement operator. A measurement operator mathematically in quantum mechanics is just a Hermitian operator. Whether or not you can realize it through the existing setups you have, beam splitters, detectors, photon counters, who knows, that sort of a thing. So a lot of creativity lies not only in sort of establishing these mathematical bounds, but actually experimentally implementing whether or not you actually have a measurement operator to finally measure what you're trying to do over here. But in general, theoretically, this can be done. You can saturate the bound. Yeah, so I think, yeah, now I think we're done. We were anyways taking questions.
There is one question in the chat related to big measurement.
You told that you
Yeah. How do I go to that chat? Chat is hidden actually. Escape? Man, there are like 50 buttons on top. Where should I click? Here? Okay. So, hi, Ashutosh. I think it will be nice if you can. You can. You can unmute yourself and share your question. Like you can discuss the question. Can you hear me? Okay, so look, weak measurement is, as we described, essentially the idea of weak measurement is as opposed to the projective measurement, which completely collapses the state in an eigenstate. Weak measurement is you don't disturb the system much. At the same time, you don't extract the same amount of information. So for example, if I have a wave function, a very strong measurement would be collapsing it as a delta function. That would be a very strong measurement. Then I would know exactly, of course, my momentum uncertainty would be very large, but I'll know, where the position is. The weak measurement would be, measuring it in some sort of an envelope. I roughly know it's there, that sort of a thing. So that's the idea of a weak measurement. So Ashutosh asked that, can Fisher information be used to put a bound on the number of weak measurements required to reconstruct a state? So, okay, so we have to step back a bit. What does he mean about the question? So see, till now we were doing metrology, which was measuring one parameter. Ashutosh seems to be talking about tomography, which is measuring the entire quantum state, not one parameter. So in some sense, quantum tomography is the ultimate quantum metrology. A quantum state has got, so for example, if you have a state on a block sphere, it has got 3 components to it, X, Y, Z. So you got 3 parameters. Yeah. So you'll have, in general, you'll have d squared minus 1 parameters for a general d-dimensional quantum state. So what Ashutosh seems to be asking is that, can there be a scheme, or can I put a bound on sort of approximately measuring these components and measuring these d squared minus 1 components of that vector of that space? That sort of is the question. Yeah, I mean, those bounds, Ashutosh, would depend upon how weak your measurement is, basically. So when you talk about number of weak measurements, it's, if I have a measurement which is so weak, I might need infinite of them, basically. The idea is that the limit of the number of measurements times the information I'm getting from the measurement should converge to a finite quantity. Now, if my measurements go to 0, in the sense that the strength goes to 0, in the sense that I've got such a feeble measurement that in each measurement I am virtually getting no information, well, then I need infinite number of.
But then usually there is a bound of d square, but because of d.
No. So see, the bound of d square minus 1 is a geometric bound. The vector resides in a Hilbert space of dimension d squared minus 1, which means that I need measurements in d squared minus 1 independent directions. So that number of measurements, d squared minus 1, is coming from the geometry. If I am on a block sphere, I need sigma x, sigma y, sigma z expectation values. Then I'll be able to construct a block vector. So this number of measurements, d squared minus 1, is coming from the geometry of the vector. The weakness is how strongly in each of those directions I am measuring. That can actually be infinity also, actually. Because let's say I'm getting hopelessly 0 information. So I need many more.
So those weak measurements are done through cross operators.
Well, you can have POVMs, cross operators. You can have, yeah. So a lot of formalisms for those kind of things. But that's sort of easy. I mean, that's how we learn physics, right? We measure physics very weakly, understand a little bit, and we do it infinite number of times, over and over years, things like that. So so physics for me is a weak measurement. Yeah, but that's the idea. Okay, any yeah.
Layperson.
Sure.
For example, an IBM computer. What is measured and how exactly is it measured? What parameter and what's measured? A real world or different kinds of computers, quantum computers.
Yeah. So I think in an IBM computer, first of all, I think it works on a circuit model. You have, the wires going, which represent your quantum states. Then you have these gates. which basically means that you are, they are pulses, but essentially you're rotating this vector in some space. And finally, this vector rotates. The whole quantum computation is a journey of a vector rotating the way you want it to rotate. And you measure the amplitudes. And what's happening due to the beautiful nature of the quantum interference we are talking in, that the right answers have a higher probability of being measured than the incorrect answers. So for example, in a search, what will happen through these rotations is that slowly you're going to converge to the right answer. Your vector would have more support over the right answer versus the wrong answer. And then when you measure the vector, you say, okay, this is where the thing is actually. So that sort of is what's happening in an IBM computer or something. You're measuring, ultimately, you're measuring the quantum state to be in a particular state, but that depends upon the probability amplitude. And that probability amplitude is mapped to the right answer of the quantum computer.
And measurement is electrical. Actually, in reality, we're measuring the electrical.
Yeah. So I mean, so the quantum computer is wherever it is, like, IBM, TJ Watson Labs or something like that. Yeah. So that measurement would be, some sort of a current in a circuit or something like that. It could be, in our metrology protocol, there would be actual clicks on the detector, click, 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 click. And then we see what's the difference between the clicks in this arm versus this arm. And then we invert that measurement record to say, oh, okay, so this was the value of the parameter.
And same for other kinds of quantum computers, there are different like.
Yeah. So ultimately, it would boil down to any measurement on a real line. And then we infer that information the way we want to infer that information. Yeah.
So basically, we can now design a Hamiltonian and state evolving.
Yeah.
I mean, I'm telling that we need to design a Hamiltonian. So the correlation between those is very precise. So the states evolves precise. That's why the metrology.
Yeah. So, people talk about these quantum speed limits, for example. So your state and the Hamiltonian should be in such a way that the speed with which the state is departing should be the maximum. That sort of is the idea, actually. So whether that enhancement is coming through state preparation, whether it's coming through dynamics, that's up to your design.
Or both.
It can be both. Yeah. So yeah.
Can you elaborate more on what is this speed?
So basically, speed limit is the derivative. You take the so for example, we talked about these wave functions. How the distance between a probability distribution is changing when you change the parameter. That's analogous to a speed, right? How fast this probability distribution is. So those are called as quantum speed limits or something like that. So that sort of is the idea. If your parameter is highly sensitive, your probability distribution is changing so that the distinguishability is easy. That's a speed limit. Or that's in some sense a speed.
This derivative is with time only?
No, it was with respect to a parameter. Yeah. Time is only one parameter, but in general, if you generalize the notion of an evolution, it can be evolution with respect to a parameter also. That's what we were doing, so this sort of a thing. So it's going in the parameter space. Your parameter is embedded in the quantum state. How rapidly this quantum state is changing with respect to this parameter. So it's a motion in the space, actually. Yeah.
If your Fisher information becomes zero, you need to have an infinite variance.
Yeah, that means you have no information, basically.
So that means that the state does not depend on the parameter at all?
Yeah, that's a good question. Or you're making a hopeless measurement. I can be measuring an identity operator. And so that's, I'm not making any measurement in some sense or something like that. So so it can be either, it doesn't depend on the parameter, or my measurement does serious problems.
So could it also be that the state was evolving with time, that the time that we are measuring it, the variance is going to be.
Yeah, but we calibrate our instruments so that we don't have those kind of things. We calibrate them and measure the fringe patterns at where they are most sensitive and things like that. So we avoid those things. But I think her question was, despite all this thing, if it is zero, then it's not even a measurement, actually. So
is there an optimal measurement scheme for all theta, all parameters, or is it experimentally for everything?
No, it's experimentally. See, for example, we have in our campus, we have people doing photon detections. We have people doing NV centers or diamond. So they are these quantum objects in diamond. So they have other kind of measurement schemes. then so it might depend very much from experiment to experiment. This is just a mathematical formulation that a measurement in quantum mechanics is a Hermitian operator. Now, how you realize that Hermitian operator, whether it's the polarization of light, whether it's the photon number you are measuring, that's the real part in some sense. This is the math.
What is the, I'm trying to associate what you just said,
Mhm.
the information you can derive from the same.
Yeah.
So experimentally, there isn't much you can get from this. Or?
No. So you can say, so first of all, the Kramer-Rao bound or the, you give me a metrology scheme. I can tell you, okay, this is a good scheme because it is sort of, the Kramer-Rao bound is attaining some sort of scaling, I can tell you. Now, typically, our hope is that there would be existing enough technology in your lab to saturate that bound, in the sense that it could be something as simple as measuring the photons coming through each port, or it can even be some sort of a parity operator, for example. But those things can be functions of some very elementary measurement operators also, which also can be realized in some sense, that sort of a sense. So it's not saying that, this is not useful. This is also very useful. Of course, there is a creativity in designing the whole experiment, like including the measurement also.
Actually, I was by this bound.
Uh-huh.
I was thinking it should be opposite way because of the variance we have bound on the Fisher information. It's not the other way, right? Because
No. So Fisher information just tells you the best you can do.
but that Fisher information is because of the variance, not the other way. I mean, I'm just
No. This is the variance of the estimator. Estimator can be any function. I can do a stupid estimator also. My estimator would be closing my eyes on all measurements, just taking one random. That
something more intensive.
Fisher information is fundamental. How fundamentally the random variable, which depends upon a probability distribution, carries that information. My estimator can be anything I want to do, but Fisher information tells you that no matter what you do, you can't go beyond Fisher information. That's the idea.
Formalism comes by the different variable delta x.
Yeah.
And so we also saw that the Fisher information is inverse proportional to the variance. So that
For a Gaussian.
For a Gaussian.
We took a very simple example for a Gaussian. Yeah. For other funky functions, it would be something, something like that. But for a Gaussian, I mean, and it intuitively makes sense, right? Narrower the Gaussian, more information you have. Yeah.
It comes down to Dirac delta.
Yeah.
Sir?
Yeah.
You defined what a weak measurement is.
Right?
So let's say in case of photons, I'm considering two cases: measuring the polarization, measuring the photon number. Either of these.
Okay.
So if I measure, what will actually happen if I do a weak measurement in case an entangled pair of polarized photons is there? Will that weak measurement somehow affect the other entangled photon?
Yeah, it would actually. It would affect. So you're saying, so they were entangled also in the polarization thing, right? Yeah.
Polarization entanglement.
Yeah.
One is horizontally and one is like what we get out from.
Sure. Yeah. So definitely, it's going to. Definitely, it's going to have an effect. I'll have to.
And what will be the actual measurement then? What is mean by weak measurement of polarization?
Yeah. See, so weak measurement. Let's say weak measurement. So let's say so even polarization is geometrically a vector on the sphere. Basically, for a qubit, you have a block sphere. It is completely isomorphic to a Poincare sphere for polarization. You have the horizontal, vertical, elliptical polarization. All the polarizations are states on a sphere, on the Poincare sphere. So weak measurement of a polarization would be, okay, you don't pinpoint that vector exactly. You sort of know, okay, it's in the first quadrant. That would be a weak measurement of polarization. You're getting an imprecise information about polarization, basically. You got my point? So that sort of is you can visualize it. So yeah, so geometrically, when your physical quantities are not precise, you have a distribution about that sort of a position. That's your weak measurement. So nothing
that will automatically tell me about the other pair of the another precision I get.
in that much precision, that sort of thing. Yeah.
And final measurement should be in that precision, or it can be opposite.
Final measurement should be. What do you mean should be?
I mean, let's say I measure the polarization for the entangled pair. Photon A has got somewhere in the second quadrant, and automatically tells me that the particular should be in the fourth quadrant. So now, after some time, I make full measurement, not a weak measurement, a proper measurement. So both of these states should collapse in the second and fourth.
Yeah, see, I'll have to think about it, because see, measurement is also introducing a lot of disturbance. So for example, when you're measuring things, you're actually collapsing and you're getting a lot of uncertainty in the other sort of a thing also. But your question is that, okay, I am sequentially measuring things. So sequentially, if one of them becomes precise, the other would also become precise. That sort of is my intuition. I mean, makes sense. That would be, so, as far as Ashutosh's question was also, a weak measurement over a long time, that's like a projective measurement, basically. Eventually you get a precise information. That sort of thing,
Basically, we do the measurement reversal also on the second qubit. That we increase the fidelity of the entangled pair.
Measurement reversal.
Yeah. First, we measure the we do the measurement weak measurement on the first particle. And we do the then measurement reversal on the second particle.
Okay, I am not very familiar with this term measurement reversal.
Yeah, that the reverse measurement is done on the second particle.
Okay. What do you mean reverse measurement? You are measuring some other operator or something like that. Yeah. Is that so? See, because measurement in my mind is an irreversible process. Once the information is in my brain, it's irreversible.
Like reverse concept is also there. That is done in the other particle, so that we increase the fidelity of the pair of the entangled.
I see. I am not very familiar with that. Maybe we are just disagreeing in the semantics. Like, what do you mean by a reversal? I see. No, but this is an English word, weak measurement reversal. Mathematically, what does it mean? We have to discuss it, like, that sort of a thing. I mean, unitaries are reversible. Measurement is something you collapse.
Measurements, the pure wave operators that we use.
No, but even then, even that's irreversible. Once you have the information, you have the information. It's not reversible. That's the difference between a measurement and dynamics in some sense. Even through a Stern-Gerlach apparatus, you can send things, but you can use two Stern-Gerlachs to actually get them back. But that's not a measurement. That's still dynamics happening.
In the literature, they are using the term weak measurement reversal.
But what operator do they assign it to? I see. Yeah. So I think we should talk about the operator which you're talking about.
They are trying to increase the fidelity of this entangled pair and then do the teleportation of that.
I see.
It is
interesting.
Alternative for the entanglement distillation and the
I see.
Quantum error correction.
I see.
We don't need extra resources for that.
I see.
Using the same pair, we can increase the fidelity of communication.
I see. Interesting. I haven't read them.
Again, weak measurement we can do on the two things. Either we can do it on the state which we want to transmit, or on the environment which is associated with our system.
I see.
So there are two concepts out there.
I see. I'll have to read them.
Environment assisted measurement or the state assisted measurement.
I see. Who are the authors?
Authors I don't remember, but there are papers.
I see. I think we're done here.
Okay. So tell them we'll come back at 2 for the afternoon lab session.
Okay. Okay. Hi guys. Online. So you guys come back at 2. Can you hear us?
Message.
Yeah, I can put a message. Can you hear us?
Yes.
So I need to type here, right? Okay. Mouse doesn't seem to work. Yeah. So please come at 2. So 2 p.m. is your lab session.
So guys, lunch might take around like 12:45. I mean, raining, so.
Oh, it's raining?
You have to give us some time because usually it doesn't come before. It's supposed to be 1, so usually they try to bring it by 12:45. I've told them to come by 12:45. But these